everyone, today we're going to be using properties of radicals to simplify and write radical expressions in simplest form. So when we're simplifying radical expressions, we need to know what does it mean for it to be simplified. It says an expression involving a radical with index n is in simplest form when these three conditions are met. Okay, so here are the conditions. It says no radicand can have perfect nth powers as factors other than 1. So for example, if I've got something like the square root of 18, that's not simplified because 18 does have a factor that is a perfect number. Okay, so we have to make sure that we keep reducing until what's under the radical doesn't have any factors that are perfect. Okay, like 2 doesn't have any perfect factors except for 1, right? 1 is the only perfect square that it would be divisible by. No radicands can contain fractions. Okay, so you don't want any fractions under the radical. And it says no radicals appear in the denominator of a fraction. Okay, it says to meet the last two conditions, we're going to rationalize the denominator by multiplying the expression by an appropriate form of 1 that eliminates the radical from the denominator. Okay, in this section, we're only going to worry about rationalizing square roots, since that's something that you learned in geometry. But in future lessons, we'll talk about how to rationalize cube roots, fourth roots, etc. Okay, it says, please note, if the index is the same, you can multiply or divide the value under the radical, and the index does not change. So you can see that if, in this case, let me look at this example, the index is the root, right? If it's the same, then you can go ahead and multiply the values that are under the root together. Notice that the index does not change, though. It's still a cube root. Okay, same thing here. If I have 2 fourth roots, I can divide, but notice the index does not change. It's still a fourth root, right? We divide the 162 by 2, we get fourth root of 81, and that would reduce to 3. Okay, so those are our product and quotient properties. Just make sure that the index does not change. Another note, we're going to multiply like parts together and simplify. What does it mean to be a like part? It says multiply parts outside the radical with other parts outside the radical. Multiply parts under the radical with only other parts that are under the radical. Okay? So you have to keep in mind, outsides only get multiplied with outsides, and what's under the radical only gets multiplied by what's under the radical. You can also simplify first if you want and then multiply. Either order works. So in example 2, I went ahead and I just copied our reference sheet, and I'm going to let it float around here as we answer these problems. We're going to start using the properties of radicals to simplify the expressions. Here we've got the cube root of 135. So looking at the cube root of 135, I know that I'm going to be looking for perfect cubes that 135 is divisible by. If I look at my list over here of perfect cubes, is 135 a perfect cube? It doesn't look like it is. It falls somewhere in between 125 and 216. So what's the largest number that 135 would be divisible by that is a perfect cube? 125 doesn't work. 64 doesn't work. 27, I think, does work. This can be broken down into the cube root of 27 times 5, right, where 27 is the perfect cube. So I'm going to underline it. And if I take the cube root of 27, what would that be? 3. So I'll have 3 times the cube root of 5. Okay, awesome. Let's go ahead and take a look at the next one. I'm just going to move this out of the way. Notice that these are both square roots, so I can multiply straight across. 10 times 14 is going to be 140. And y times y is going to be y squared. Now, what am I looking for? This is a square root, so we're looking for factors that are perfect squares. Is 140 a perfect square? Do you see that in the list of perfect squares? No. So I have to figure out what is the largest perfect square that it would be divisible by. Let's see, it's not divisible by 100, it's not divisible by 81. I'm just checking each one of these to see if it divides evenly. Finally, we get to 4, and it is divisible by 4. I can break that into 4 times 35, which 35 only breaks down into 7 and 5. So I know that works there. Okay, and we've got y squared. I'm going to note that 4 is the perfect square and that y squared is the perfect square. Okay, we're going to simplify the perfect parts. Let me just throw this out of the way so I can zoom in and finish simplifying this. Square root of 4 is going to be 2. Square root of y squared is going to be y, right? Because y times y is y squared. Okay, and then 35 is not perfect, so it has to stay underneath the radical. Okay, and I cannot break 35 down any further. There is no perfect square that 35 is divisible by other than 1. All right, so here we've got cube roots again. They're both cube roots, so the index is not going to change. We're going to leave it as a cube root. We multiply the outer parts together, so we get -8. And then we multiply the inner parts together, which 12 times 18 is 216, I believe. Let me grab my calculator and just make sure. 12 times 18 is 216, correct. All right, now is 216 a perfect cube? Look at your list of perfect cubes. I'll make them a little bit bigger. 216 is a perfect cube. Okay, what's 216 a perfect cube of? 216 is a perfect cube of 6. So I'm going to make this -8 times 6. Right? You could underline it if you wanted to. That's what we simplified because it was perfect. So that came out of the radical. And so we get -48 for that question. All right, let's go on to part D. Go ahead and move that out of the way. Okay, in this example D, they are both cube roots, so I'm just going to multiply the outer parts together and get 6. And then we'll multiply the parts that are under the roots together. So 9m times 9m squared would be 81m cubed. Okay, I am looking for perfect cubes that 81 and m cubed are divisible by because I have a cube root. So looking at my list of perfect cubes, it does not look like 81 is a perfect cube. So what is the largest perfect cube that 81 would be divisible by? 81 is not divisible by 64, but I think it is divisible by 27. 27 times what would be 81? That'd be times 3, where 27 is a perfect cube. And then m cubed is also a perfect cube, right? M times m times m is m cubed. Simplifying, we get 6 times, let's see, that would be 3. And the cube root of m cubed is m. And then underneath the cube root, we're going to have to keep that 3 under there because it is not perfect. So I end up with 18m times the cube root of 3. Okay, wonderful. Go ahead and move this out of the way again. Okay, we have cube roots here, so I'll multiply. 3 times 36 is going to give us 108. Y cubed times nothing, we just get y cubed. And then x times nothing is just x. Okay, so is 108 a perfect cube? I don't see that in our list. It falls here, so is 108 divisible by 64? It is not. Is 108 divisible by 27? It is. It's going to be 27 times 4. Where 27 is a perfect cube. Y cubed is also a perfect cube, but x is not. Okay, so simplifying each part, the cube root of 27 is 3. The cube root of y cubed is y. And then we have to keep the 4 and the x under the cube root because those weren't perfect. Notice that I still am writing a 3 in. Okay, if you put a square root, it's wrong. So you have to make sure you're using the correct index. Over here, these are both 4th roots, so I'm just going to multiply the parts that are under. 5 times 125 is going to give us 625. Then we'll have our x to the 8th, y to the 12th, and z to the 4th. Okay, what is the fourth root of 625? Well, let's see, we're looking at perfect fourths now, right? I know I'm looking at perfect fourths because that was a fourth root. So 625 is a perfect fourth. What's it a perfect fourth of? 5. Okay, I'm going to underline that because it is perfect. Is x to the 8th perfect? Well, let's see. We want something a number that we can multiply by itself 4 times to get x to the 8th. What about x squared? Couldn't I do x squared times x squared times x squared times x squared and get x to the 8th, right? That'd be 2, 4, 6, 8. So that is perfect. What about y to the 12th? Couldn't I do, what is it? Y cubed, y cubed, y cubed, y cubed 4 times? 3, 6, 7, 8, 9, 10, 11, 12. Yep, that works. And z to the 4th would be z times z times z times z. So yeah, these are all perfect, really. Okay, so let me get my perfect numbers out of the way. I'll zoom in here. We said that 625 was a perfect fourth of 5. That comes out. We said that x to the 8th was a perfect fourth of x squared. We said y to the 12th was a perfect fourth of y cubed. And we said z to the 4th was a perfect fourth of z. Okay. An easy trick is you can do 8 divided by 4 and get 2. You can do 12 divided by 4 and get 3. You can do 4 divided by 4 and get 1. You see, that's a nice fast trick to simplify those perfect fourths for your variables. Okay, so there's that. Let's go down here. Move this out of the way. Now, in this case, we have some different indexes. Here we've got square roots, and here we've got cube roots. So remember, the index has to be the same in order for you to multiply those parts together. So I'm going to multiply the square roots together. So we'll get the square root of 18 times, then we'll multiply the cube roots together. We get the cube root of 27, which that's actually nice. The cube root of 27 is just 3. 18 is not a perfect square, but we can break it down into 9 times 2, where 9 is perfect. Square rooting that, we get 3 root 2. Okay, so I've got two parts that really we're multiplying together. I'll write this a little bit nicer, right? 3 radical 2 times 3. So we end up with 9 square root 2 as our answer there. All right, in this case, it's the same thing. I've got 2 square roots, and then I've got a fourth root. So I cannot multiply the fourth root by the square roots. If I multiply the square roots together, we get 15 times 3, which 15 times 3 is going to be 45. So we get 45. It's going to be y squared when we multiplied y times y. And we have times the fourth root of 16y to the 4th. Now let's try to simplify. Over here on this left-hand side, we're looking for perfect squares that 45 would be divisible by, because we're dealing with a square root. Okay, so if I'm thinking about perfect squares, 45 is right here, so I would say that 45, the largest perfect square it'd be divisible by would be 9. We'll break it into 9 times 5, where 9 is perfect, and y squared is perfect, right? It's a perfect square of y, times. Okay, now in this radical, we're looking for something different. We're looking for perfect fourths. So look at your list of perfect fourths. Is 16 in that list? Yeah, actually 16 is in that list. 16 is perfect fourth of 2. So I'll say, yeah, it's perfect. And y to the 4th would be a perfect fourth of y. So both of those are perfect. So I'm just going to underline them, and we're going to simplify those parts. Okay, so simplifying, the square root of 9 is 3. The square root of y squared is y. 5's left under the radical. Times the fourth root of 16, we said was 2. And the fourth root of y to the 4th is going to be y. Okay, multiply parts that are outside the radical by other parts outside the radical. So I'm going to multiply the 3y by the 2y since those are both outside of the radical. So we get 6y squared times the square root of 5. Okay. Over here in I, these indexes are not the same. We've got a square root and we've got a fourth root. So I cannot multiply them right now. Here's a trick. I want you to rewrite it in rational exponent form. So my power over root here would be 2 to the 1/2. And here my power over root would be 2 to the 1/4. And now that we have like bases, when we multiply, we can add those exponents. So I'm going to keep the base the same, and I'm going to add the exponents. 1/2 plus 1/4. 1/2 is the same thing as 2/4. So we'll have 2/4 plus 1/4. So we end up with 2 to the 3/4. Okay, or if you want to write it as the fourth root of 2 cubed, you could write it like that. Or if you want to write it as the fourth root of 8, since that's what 2 cubed is, you can write it like that. Okay, but that's our workaround. And I would make a big star that this is a trick if your index is not the same. Trick if your index is not the same, you just use the rational exponent form. Convert it into rational exponent form. It's a nice workaround. Alrighty, down here, let's go ahead and move this out of the way. The index is the same, so we can multiply. So I'd have x plus 2y times x minus 2y. And really, there's not much simplification I can do. Like, that's what we're going to have. Unless you want to multiply it out. If you multiply it out, we're going to get x squared minus 2xy plus 2xy, then minus 4y squared, which if you combine like terms, we get x squared minus 4y squared. So I guess you could write your answer like that. Really, I don't think it's worthwhile to even multiply it out. Okay, that form's not any more simplified. So I'd probably just leave it in factored form. The reason I leave it in factored form is because if it's multiplied out like this, you cannot do this. You cannot just square root individual parts. You can't do that. If I'm ever given the standard form of something, I always try to factor it because that's when we're going to be able to simplify it as if it's in factored form. For example, over here, if I multiplied these like parts, we'd have x plus 2y times x plus 2y. And that would be x plus 2y squared. See how now it's factored and the square undoes the square root, or vice versa. The square root undoes the square. And so I'm just left with x plus 2y outside the radical, right? The square root of x plus 2y squared is x plus 2y, okay? But we like it to be in factored form before we can reduce that. So just be careful there. All right, let's go on to dividing now. It says divide and or multiply parts that are alike. For example, if you're given this expression, the 4 can be divided by 2 and the radical 10 can be divided by the radical 5. Okay, you always divide out parts outside the radical with other parts outside the radical. Divide parts under the radical with other parts under the radical. So looking at this first example here, they're both 4 for the index, so I can just divide those parts. Radical, the fourth root of 80 divided by the fourth root of 5 is going to end up giving me fourth root of 16, which 16 is a perfect fourth. It's a perfect fourth of 2. Okay, 2 to the fourth is 16. So that's it. That's really it on the first one. The second one, they're both under the square root. We just simplify. 25 divided by 5 is 5. Done. Okay, I can't simplify the square root of 5 any further. For part C, let's see, what's 1,000 divided by 27? That is, ooh, that's a decimal. That's like 37.037, blah, blah, blah. So maybe I don't want to reduce it like that. Here's another option. When you're working with roots, rather than it all being under the same root, you can break it up so that 1000 a cubed on top is under a cube root, and the 27b cubed is under a cube root. Let's try to simplify the top and bottom individually. 1000 is actually a perfect cube. What's it a perfect cube of? I think it's 10. Yeah, 10 times 10 times 10. What's a cubed a perfect cube of? Just a, so that's done. What's 27 a perfect cube of? 3. And what's b cubed a perfect cube of? B. Okay, and I can't reduce that anymore. 10 thirds is just 10 thirds. Okay, so there's that one. Over here, let's try to divide 4 by 2. That's going to give me 2. And we'll try to divide the cube root of 81 by the cube root of 3. I can only do that because the index is the same. So I get the cube root of, I think that's 27, which that's perfect, right? So that'll be 2 times 3, which is 6 right there. All right, down here, ooh, we're getting fifth roots now. So we're going to be looking for perfect fifths. Because they're both fifth roots, let's divide 64 by 2. That's going to give me the fifth root of 32. Let's try to divide a squared by a to the 7th. Where are there more a's? There are going to be more a's on the bottom, right? Because that's a to the 7th. How many more a's are on the bottom than on the top? 5. 5 more a's. So I'm going to make this a to the 5th stay on the bottom since there were 5 more on the bottom. If I'm looking at the b's, we have b to the 6th over b to the 1st, right? Where are there more b's? There's more b's on top. How many more? 5 more, right? Because this is really b to the 1st. Okay, so it's going to look something like this. So now let's see if I can reduce it. 32 is a perfect fifth. What's 32 a perfect fifth of? Well, 1 to the 5th is 1, 2 to the 5th is 32. There we go. So I'm going to say that that's 2. What's b to the 5th a perfect fifth of? 5 divided by 5, we get b to the 1st. What's a to the 5th a perfect fifth of? 5 divided by 5, we get a to the 1st, right? The fifth root undoes the fifth power. So we get 2b over a. For this one, they're both square roots. Let's try to do 189 divided by 7 and see where that gets us. That does work. We can do that. That's going to be the square root of 27. What's x to the 4th divided by x squared? That's going to be an x squared on top, right? And what about y to the 7 divided by y? There are 6 more on top, so I'll put y to the 6th. Okay, and this is all over 1, okay, but that's implied, so I'm just going to erase that. All right, I'm looking for perfect squares because we're dealing with a square root. So I'm going to break 27 up into 9 and 3, where 9's perfect. Let's see, x squared is a perfect square of x, and y to the 6th is a perfect square, right? Isn't y cubed times y cubed y to the 6th? Right? Or you can think of it like 6 divided by 2 would be 3, y cubed, right? So let's reduce the parts that are perfect. The square root of 9 is 3, the square root of x squared is x, and the square root of y to the 6th is going to be y cubed. And then we've got this little lonely 3 left under the square root. Okay, just a couple more examples. These examples take us back to geometry. These are geometry throwbacks. Can't divide 7 by 3 because one's outside the radical and one's under. And even if we could, 7's not divisible by 3. Why don't I like the way this is written? I don't like the radical in the denominator. Ew. You cannot leave a radical in the denominator. So what I'm going to do is I'm going to do something called rationalizing, right? I'm going to multiply the top and bottom by the square root of 3. Okay, so if I multiply 7 times the root of 3, I get 7 root 3. If I multiply radical 3 times radical 3, I get radical 9, which is nice because see how now I have a perfect square under the square root? That means I can reduce it. And see how no more? I have a radical no more, right? I got rid of the radical in the denominator. There's no longer radical in the denominator, which is what I was looking for. I wanted to rewrite the expression so that there was no longer going to be a radical in the denominator. Okay, over here, let's try to reduce this. A cubed divided by a is going to be a squared. Radical 3 over radical 9. Let's see, 3/9 is 1/3. So I'm going to have radical 3 still down there in the bottom, right? And I don't like to leave it like that because I have a radical in the denominator. So I'm going to multiply the top by radical 3 and the bottom by radical 3. Okay, so I get a squared radical 3 up top. Again, here I get square root of 9 in the bottom. And square root of 9 reduces to 3 because it's perfect. Right? I'm multiplying by something that's going to give us a perfect square under the square root. And I like that because it gets rid of my radical in the denominator. Now, here's the question. Can I take square root of 3 and divide it by 3 and get 1? No, because I can't do that because this 3 is under a radical and this 3 is outside of a radical. So you cannot reduce those parts.